In Australia, 4.4 million people live with a physical disability, with 1,800,000 people employing commercially off-the-shelf wheelchairs and powered wheelchairs. These devices generally operate through physical control through the user's hands or with a joystick. However, individual symptoms can vary in severity and consistency, with up to 40% of users finding normal operation difficult or near impossible, therefore rendering the benefits of mobility devices inaccessible for the entire spectrum of disabilities where a user's upper extremities are severely affected. Hi, my name's Hao Nguyen, and I'm presenting my undergraduate thesis topic, Enabling Autonomous Navigation for Existing Powered Wheelchairs in Urban Environments, with my supervisor, Dr. Ali Haider Gurktwan. So, what can we do to enable people with severe disabilities who cannot use a powered wheelchair joystick to travel independently? Presenting Swan, your smart wheelchair assistant for autonomous navigation. Swan is an add-on device for existing powered wheelchair platforms that provides an alternative set of control modalities. Swan is highly beneficial to users with different levels of disabilities and addresses the constraints of singular joystick control. Swan's system architecture consists of 5 main modules: the main control unit, obstacle detection, joystick controller, speech control, and the mission planning and teleoperation application. Swan is contained within 3 component enclosures. The primary enclosure houses the main computing unit, RGBD camera, and is mounted under the armrest, with the joystick controller positioned on top of the joystick unit. The second enclosure is placed on the footrest, containing front-facing ultrasonic sensors and a 2D LiDAR. Finally, the third enclosure is placed on the back, with rear-facing ultrasonic sensors. On the graphical user interface, users can define a series of waypoints. Each waypoint can be dragged or deleted and execute user-defined actions such as stop, pause, or continue upon arrival. Line segments between each are configurable for desired speed. Saving and loading of missions is available from the local server onboard Swan or a remotely hosted server. And sensor data logging can be initiated with operational parameters such as default speed, maximum path deviation, and PID gains also configurable. To enable control for Swan, first the kinematic model of a powered wheelchair is derived. The following equations, which we unfortunately do not have the time to explore in depth, relate the linear and angular velocities of the wheelchair to changes in pose within the world frame. To initiate powered wheelchair control, on the joystick unit is a 3D printed detachable joystick controller with 2 servo motors. Joystick actuation is initiated from the servo motors with angular displacements proportional to wheelchair linear and angular velocities. Here we see Swan autonomously navigating a predefined path through Cadigal Green at the University of Sydney campus. The route is initiated and defined through the mission planning and teleoperation graphical user interface. Path tracking for autonomous navigation is enabled through the Pure Pursuit algorithm. The equations here derive how Pure Pursuit geometrically calculates the curvature that moves the vehicle to the desired goal waypoint. Its operation is quite analogous to how humans look ahead at certain distances to track roads while driving. To validate performance, field tests of 341 meters at Cadigal Green presented effective handling against various footpath characteristics. Further validation was required for longer missions, better representing daily use case scenarios, with a 1.21 kilometer mission through Victoria Park demonstrated without human intervention. Teleoperation is available for users and caregivers through a virtual joystick, offering less physically demanding control. In the top right hand corner, you can see that live RGB or RGBD video streaming is selectable and adjustable based on available bandwidth, given that a human operator can still discern obstacles at lower resolution and frame rates. Additionally, speech control allows user operation through the recognition of several command types, for example, navigational commands.
Turn right 45 degrees.
Turning right. Going forward.
Speech control is enabled through a dual speech processing architecture featuring 2 natural language platforms, Dialogflow and Raspi. This prioritizes better performance, employs redundancy for safety, and ensures functionality outdoors, as Dialogflow requires stable internet connectivity for cloud processing, unlike Raspi. 13 unique speech commands were tested, with results supporting the choice to prioritize execution based on intention confidence. Obstacle detection maximizes user safety to avoid pedestrian and obstacle collisions during navigation. Safety regions are constructed for safer operation, with 3 regions indicating the obstacle proximity, initiating speed adjustments or an emergency stop if triggered. Swan has validated its capacity to facilitate independent travel for people with severe disabilities who are unable to use the joystick of a powered wheelchair. Autonomous navigation and obstacle detection is demonstrated through high-density pedestrian environments. Mission planning and teleoperation is available through the GUI with integrated speech control, and future work with Swan will focus on the integration of additional control modalities, in particular gaze tracking. With new doors open for people whose options have always been limited, hopefully sometime in the future you'll see Swan out near you.